Hello friends, today we're going to be doing lesson 2.1, which is an introduction to arithmetic and geometric sequences. So let's get into it. So a sequence, the way this works, right? A sequence, filling in the notes, is a function from the whole numbers to the real numbers. Okay. So it's a function, and we're only putting in whole numbers, 1, 2, 3, 4, etc. But we're getting any number out. It could be like a decimal or a fraction, something like that. So here's an example that they give you. It says, consider the sequence defined by a sub n equals 4n minus 3. Find a1 and a7. Okay, here's what they mean by this. An means so for example, a sub 1, this means the first number in the sequence. Okay, it's not the original value, it's not a sub 0, it's the first value. So we can graph this too, and this would just look like points. Instead of it being a continuous line, it's just going to be individual points, and a sub 1 is going to be the y value when x equals 1. We can look at it that way. All right, and so all we're doing is we're plugging 1 in for n. So this becomes a sub 1 equals 4 times 1 minus 3. Okay, and this turns out to be 1. A sub 7 is 4 times 7 minus 3. And so this is going to be 25. Right? 4 times 7 is 28. Minus 3 is 25. Okay, so what's going on here? Let's talk about some of the notation, etc. Arithmetic sequences, different from geometric sequences. Arithmetic sequences work like lines, where there's a common difference between the terms. Okay, and that difference is, in our example, the 4 is the difference. Okay, and so the formula that's given to us is a sub n equals a naught plus dn. Here's the first formula. A naught would just be the original value. You can see what that value is if you put in 0, right? A sub 0 equals 0, because if we take like this example that we have here, let's go over to the side. All right, a sub n equals 4n minus 3. If we plug in 0, well, a sub 0 equals 4 times 0 minus 3. And so you can see this ends up just being 0, just negative 3. Okay, so negative 3 would be a sub 0 in this case, right? As you can see. But what if we don't have the original value? What if we don't have the output for the input of 0? If we just have some other term, if we have, say, like the 6th term, what we have then is this formula here. A sub n equals a sub k plus d times n minus k, where k is some other term in the sequence. So let's see. A sub n is the initial value. D is the common difference. A sub k is the kth term in the sequence. Okay. And like I said, it behaves like a line, like a linear function. Really, all you need to know is this second thing, because if you plug in, if k ends up being 0, then it just takes you back to the first one. So it's really the second expression that you need to kind of memorize. So here's an example. A sub n equals 3n plus 1. So we can create a little table here, n, right? So n is going to be our input, and the output is a sub n, the nth term of the sequence. And so if we put in 0, say 1, 2, 3, etc. If we put 0 into this, then we just end up with 1. If we plug 1 in, so 3 times 1 plus 1, we end up with 4. Now, from the formula, using the formula, it looks like the common difference here is 3. right? And that's how it's playing out. So we get 7 and 10, etc. So now we plot this. Now these are only points, so 0, and then we lose it after that. All right, but that's what that graph would look like. Okay, so now they give us some examples of sequences. They're asking if each sequence is arithmetic. Again, arithmetic just means a common difference between them, between the output terms. So for A, we can create a little table. Now we can already tell just kind of by the form of it, see it's got this n squared in there. This is not going to be an arithmetic sequence because this is not going to give us a common difference each time as we're going along. But we can set it up anyway. So when I plug the numbers in, for 0 I get -3, for 1 I get -2, for 2 I get 1. You can see that the differences between them are different, right? Between -3 and -2 is a difference of 1, and then -2 and 1 there's a difference of 3. So this is not arithmetic. Put an X through it. And then Sn is 6 minus 2n. So let's make a table. When we make this table, we see that there is a common difference here of -2. See, it's going down every time, and that makes sense. This has the formula. It looks like a linear function, and the difference, or the slope, is -2. And that's what we see. So this one is arithmetic, so we put a check mark on that one. For C, now we look, and what's the difference here each time? Well, going from -7 to -2 is a difference of 5. -2 to 3 is also a difference of 5. 3 to 8 is a difference of 5. Also, so this one is arithmetic because it has a common difference. That's the idea. Now for D, 1 to -2, that's a difference of -3. And then -2 to 3 is a difference of 5. So right away we know this one is not arithmetic because it's not a common difference. Example 3. Says, let A sub n be an arithmetic sequence with A sub 3 equals 8 and D equals -3. Find an expression for an and use the expression to find A12. So now we're going to be using the formula. So notice we don't have the original term, we don't have the base, and we don't have the original function. So we have to set this up, and we're going to use the one that look like this. A sub n equals A sub k plus, that look like D, n minus k. All right, so our what we're using here for k is 3, because that's the term that we have. So this is going to become A sub k, so A sub 3 is 8, plus, we know the difference is -3. We're going to leave n because we're looking for this expression where we can plug n in to find out what it's going to be, what the original function is going to look like. And so now k is 3, so n minus 3. And now we just simplify this, and we end up with, well, I'll walk you through some of the steps. Plus, let's see, -3n plus 9. And then when we simplify this, we end up with 17 minus 3n. Okay, so this means that A sub 0 would be 17. And this maintains, right, it's still in there, the difference of -3. They want us now to use this to find A12. So we just plug 12 in for n and see how it turns out. Okay, so we plug 12 in for n, and we end up with -19. Okay, example 4, let A sub n be an arithmetic sequence with A2 equals 7 and A sub 6 equals 9. Find an expression for an and use the expression to find A24. So this time, they don't even give us the difference. And so we're going to have to find the difference, but using the formula that we just used. Right? So A sub n equals A sub k plus D times n minus k. Okay, so now we have this formula, and we're going to be using A sub 2 for AK, which is kind of like our new base, and then A sub 6 for AN, and we just plug those numbers in, and we're going to have to solve for D that way. All right, so now that we've found what D is, we can use D and either A2 or A6 to put back into the formula we just used to find what A24 is going to be. Okay, so we're going to use A sub 6 as our new base for calculating A24. Okay, when we plug those numbers in, we see that 18 is what comes out as the solution. In example 5, we're given some terms of a sequence in a graph, and they want us to find the expression for A sub n and then to find A17. All right, well, just by looking at this, we can see that A sub 0 is 8. Right? And we can see that the common difference here, it's going down every time, right? I mean, you can think of it in terms of slope. It's going over 1 and down -2. So the difference is going to be -2. So our formula is going to look like this. A sub n equals the base term 8 plus -2 times n. Or you could say just 8 minus 2n. Either way, it works. So now to find this for 17. So A sub n equals 8 minus 2 times 17. When you do that in arithmetic, you get -26. That's your answer. Okay, now we're going to introduce to geometric sequences. Here, the successive terms have a common ratio. Okay, and these behave like exponential functions, except that they're not continuous, right? Exponential means that the exponent, that the variable is in the exponent. It doesn't, like x squared is not an exponential function. 2 to the x is an exponential function. So here's our base expression, gn equals g naught times r to the n. That's again when we have the base, the initial value, but we don't always have the initial value. And so this, just like in the arithmetic sequences, this other expression is very useful, right? Where r is the common ratio. So it kind of serves the same function as d in the arithmetic sequences. And k is the kth term of the sequence, right? And so here's an example that they give us where g of n equals 8 times 1/2 to the n power. Okay, and so 8 is the initial term, and you can see that because when you plug in 0, so when we have n and g of n, when you plug in 0, this would be, right, 8 to the times 1/2 to the 0 power, but anything to the 0 power is just 1, right? So the initial term here is 8. So those are the values that we get, and now let's see what this looks like when we graph it. That's what this exponential function looks like. Okay. Now, in example 6, they're saying for each of the following, determine if the sequence is geometric, and if yes, identify the common ratio. For letter A, we can tell right away that it's not geometric just by the form of the function, right? The variable n is not in the exponent. But if we were to create a table, we'll see how it turns out. So when we look at this, we see that 27 divided by 12 is just about 2. 12 divided by 3 is like 4. So it's not a common ratio between these. So now we look at the next one. And here there is an exponent in the, there is a variable in the exponent. It looks like it's the right form. So let's create the table and check it out. Okay, so now when we take a look, 16 divided by 8 is 2, 8 divided by 4 is 2, 4 divided by 2 is 2, and 2 is the common ratio. And so this makes sense. This one is a geometric sequence. Taking a look at C, if we start over here, 24 divided by 8 is 3, but then 8 divided by 12 is not 3, and 12 divided by 4 is 3, 4 divided by 6 is not 3. So this one is not a geometric sequence because they're not all following the same ratio. There's not a common ratio here. Okay, so let's check out this one. Initially, this one looks a little bit confusing. It's like negative, positive. Probably not, but let's be careful because I'm going to write this one out. I'm going to use a smaller smaller lines so we can write it all in here. So 1 divided by -2, so that's -1/2, right? And then -2 divided by 4, that's also -1/2. 4 divided by -8, write that out, 4 over -8, I'll leave the negative out front, that's also -1/2. And then -8 divided by 16, whoops, I wrote it wrong. -8 divided by 16 is also -1/2. So this one actually is a geometric sequence. There is a common ratio there. It's a terrible check mark. There we go. A little better. Let's take a look at example 7. It says, let g of n be a geometric sequence with g of 1 equals 12 and r equals 2. Find an expression for g of n and use the expression to find g4. So we're not given the initial term, but we're given what g1 is. And so we can plug this into that second expression that we have and find what the base expression should be, and then find g4. So here's that second expression filled in, right? G of n equals, so now this is the kth term, right? G of k. And so g of 1, so we're using g of 1, right? The nth. So k is what goes in there, and this is where the 1 goes in. So now we fill this in with the value for g of 1, which is 12. It's 12 times 8, which is 96. Okay. And then in example 8, they give us several terms using a graph, and so we can use this to find what G10 is. So let's take a look how we can use this. So we know that the values here, the output values you could say, are 8, 4, 2, 1, and it looks like it's going down to 1/2, a quarter, something like that. And so the common ratio here is 1/2. Okay, so R is 1/2. Good. And the initial term, right, G0 is 8. So we can write our expression as G of n equals 8 times 1/2 to the n power. And now we want to find G of 10. So G of 10 equals 8 times 1/2 to the 10 power. You do that arithmetic, you might need to use a calculator for this, but you end up with 1 over 128. Okay. So that's lesson 2.1, part 1. There is a part 2 coming later. Stay tuned for that. Don't forget to like and subscribe.